The recording is now on. Class has now officially begun. I hope you guys had a great weekend and enjoyed the homework-free weekend there. It's getting down to the end here, not a whole lot of time left. I presume that you guys received the email message that Principal Wilson sent out, where he instructed us, all of us teachers, to not give any new content after this coming Friday. So, and that's a little faster than I would have liked. We are going to have to skip a few really interesting topics as a result of that, like for instance, string theory. I was hoping to talk a little bit about string theory, but we're going to have to drop that one. But we will still be able to finish quantum mechanics, and we will also be able to do a good job on relativity, I think. But string theory and some of that other weird stuff is just going to have to go. All right, so Jaron, I see, does not like waiting until the end to do the secret phrase. So okay, I can live with that. So the force will be with you always. Okay, I can do that. So let me write it down here. Force will be with you always. Okay, so there you go. This will be today's secret phrase. The force will be with you always. Okay. Okay, so yeah, so Anna is asking what's the plan as a result of what I just said. Okay, so here's the deal. So today, Wednesday, and Friday, we will cover new material. We're going to finish quantum mechanics today. On Wednesday, we're going to go over special relativity, and on Friday, we'll go over general relativity. So then on Monday of the following week, I will give out the practice test. On Wednesday, I will go over the answers to the practice test. And then on Friday of next week, we'll have our final exam. And then after that, I don't plan to hold any more classes. And I would like you to return your books at that time, but hang on to your books until after our last midterm. Okay, so yeah, and you guys have heard about string theory and some other really interesting topics, but you know, what can you do? We're not going to be able to get to it. The official last day of school, I don't know what that's going to be, but I do know, well, basically I saw the letter that Principal Wilson sent out to you. So I don't know any more than that, okay? All right, let's move on. Okay, so I noticed when I looked at the quiz grades, I noticed that a lot more of you guys than normal retook the quiz multiple times. And some of you retook it like 5 or 6 times before you finally got a 10 on the quiz. And that's okay. I mean, I purposely set it for that. But I wondered, why did you guys have so much trouble with it? And so I went in and I looked at it. And so one of the questions that you guys had trouble with was this one. Many of you thought that the correct answer to this one was the middle one here. All of them are correct. Many of you thought that. And now it is true that all of these phrases could have been used. I mean, I think all of these phrases do a pretty good job of describing what happens. So collapse of the wave function, wave particle conversion, concentration of the wave function, wave solidifications, all of those phrases are phrases that scientists could have chosen equally well, but they didn't choose them. There's only one that they actually chose. Okay, so the one that they chose was the collapse of the wave function, or wave function collapse. The key word there being collapse. That's the word that they chose. Could they have chosen the other ones? Yes, but they didn't. This is the one they chose. Okay, also, let's see. Okay, quantum tunneling. Okay, in this case, all of those were in fact correct. Quantum tunneling is the key to how flash memory works, and it's also the first one here describes what quantum tunneling is. And then the last one, the convenient plot tool in science fiction movies. Yeah, there's a huge hole in that, and it's probably not worth taking the time to discuss it. But let me, in very briefly, I saw a science fiction movie once where the hero needed to get on the other side of a wall, and there was no way to do it. It was an impenetrable wall. So what the hero did was he leaned up against the wall, and then he waited for quantum tunneling to tunnel him across the wall. The problem with that is if quantum tunneling occurs, each individual particle of your body has to quantum tunnel separately. And so it's possible that one of the particles in his body might quantum tunnel across the rest of the wall, or across the wall, but the rest of the particles in his body aren't. I mean, they're not all going to quantum tunnel at the same time. The best you can hope for is, 1 in a billion. So, but anyway, let's not spend time on that. Okay, in which state do more people get scammed than any other state? That's Utah. Okay. Okay, so which of the following is true? Now this is the question that really gave most people the most trouble. As you can see here in blue, I like my way of describing the Heisenberg uncertainty principle better than what you're going to see if you Google it. But you need to be prepared because this is what you're going to see. So what I like to say is that the more momentum that some particle has, the more compact its wave function is going to be. And in fact, this right here, this is what I picture in my mind whenever I talk about, or whenever I think about Heisenberg uncertainty principle. And I would hope that you would as well. Okay, so the key is this equation up in the front, which is the de Broglie equation. So Louis de Broglie experimentally found that the momentum and the wavelength are inversely related, and h is the proportionality constant. So the more momentum something has, the shorter the wavelength is going to be. And if you look at these three packets here, all three of these packets contain the same number of waves, but because the wavelength is different, the packet on top is more compact, the one in the middle is more spread out, and the one at the bottom is really spread out. Okay, so this region of uncertainty here, I just kind of arbitrarily picked the 95% line. So I say, if you are willing to accept 90% probability of finding the wave, then I can tell you that a fast-moving electron, there's a 95% probability that your detector will go ding if you put your detector in this small region here. But if the electron is moving more slowly, then you got to go with the bigger region of uncertainty. And if it's moving really slowly, then you got a huge region of uncertainty. Okay, so the uncertainty about where the electron is inversely related to the momentum. That's the way I like to say it. Okay, but what you're going to find out is it's going to be something like this. In the literature, more common. So a lot of people got this problem wrong, and it took them like 4 tries before they finally guessed right. Okay, so the way I recommend you approach it is look at the circles I have here in red. Okay, so this answer right here claims more momentum means more spread out. Well, go back and look at this. That's clearly wrong. Because of our equation up here, more momentum means less spread out, it means more compact, all right? So answer number 2 and answer number 3, we can rule those out because it's clearly, obviously, more momentum does not mean more spread out. Okay, so those 2 are definitely wrong. Okay, so that leaves us with 2 answers. And so you guys know that when you take multiple choice tests, this is the way to do it, right? There's always going to be at least 1 and sometimes 2 questions that are obviously wrong, or answers. At least 1 or 2 answers that are obviously wrong. So these are the 2 that are obviously wrong. Okay, so now we need to decide between the remaining ones. So this one says more compact it is, the harder it is to determine its position, where this one says the more compact it is, the easier. Well, okay, the more compact it is, that means the uncertainty about where the thing is smaller. So looking at that, you can rule out this one, and so you can say, well, the bottom one there, that's the right answer. So this is the way to approach pretty much all multiple choice questions. I recommend you practice with that. Okay, and then the secret name was, of course, George. All right, so there was no homework to go over, so we don't need to spend anything on that. So we can now jump into the new material, but let me pause for just a second and say, does anybody have any questions? Especially, questions about this one right up here or anything else from the quiz. I'll give you a few seconds to type something in. Okay, I'm not seeing anything being typed in, so I will take that to mean no questions. All right, so the plan today is we will finish up quantum mechanics. Although in reality, on Wednesday when we talk about relativity and quantum mechanics are very closely related. Relativity would not occur if it weren't for quantum mechanics, but you know what I mean. We're gonna finish up quantum mechanics right now. Okay, so we're going to go into chapter 28. Now, there is a lot of stuff in chapter 28 that I am not going to focus on. There's just one key concept, really, that I want to emphasize in chapter 28. And so I'm going to go over it now, and then their homework tonight will be just about this one concept. So you don't need to read the entire chapter 28. Just focus in on the things that relate to what I'm about to talk about. All right, so when you were in junior high school, your science teacher probably told you to think about the atom as if it was a miniature solar system, where in place of the sun, we have the nucleus of the atom. That's where the protons and neutrons are. And then the planets here, okay, those are essentially the electrons. Okay, so most junior high school science teachers, that's the way they present it. And in fact, that is a useful thing to think about to a certain degree. But once you start getting into science really deep, this solar system model breaks down. And so that's what we're going to talk about right now as it breaks down. So Jaron is saying that it's incorrect. Yeah, I know, but it's a simple it's a simple model that is useful to in some circumstances, but it is not actually what happens. And so what we're going to do today is we're going to talk about what does actually happen, right? But let's talk about the solar system here. So let's take the planet Saturn here. So if we were to somehow reach in there with a great big hand and give Saturn a little bit of a push, we somehow increase the amount of energy that Saturn has. Do you guys see that what the Saturn would do? It would go into a slightly larger orbit. Okay, if we give it a little more energy, it'll go into an orbit that's got a little bit bigger radius. If we give it a little bit more energy still, it goes into yet another bigger. So basically in between the orbits of the planets, okay, those regions there, they are not forbidden regions. You could most definitely have a planet anywhere out here, okay? Whereas hopefully you know from your chemistry class, that's not the way atoms work. Atoms, they have forbidden regions. If the electrons that orbit them, okay? So if you had an electron in this orbit right here, and the next higher allowed orbit is this one here, that electron cannot exist in between. Okay, you can either be here or here, but you cannot exist in between. So I know that Coach Miller talked about this in his chemistry class. He may not have gone into the reasons why, or if he did, he may have just superficially talked about it. Well, today we're going to not only go into the reasons why, but we're actually going to do the calculations. We are going to start with first principles, and we're going to calculate what the allowed orbitals are, at least for the hydrogen atom. The other atoms get a little more complicated, but the hydrogen atom can. All right, so here are a couple of the allowed orbitals. Now, you're going to have to use your imagination to assume that there's a nucleus in the middle here. Okay, so this is the orbit of the electrons, and so it turns out that you will only have a stable orbit if the wavelength of the electron, or let me rephrase that, if the circumference of the orbit is equal to an integer number of wavelengths, because we now know that electrons are not little marbles, they're actually waves, okay? And so when this electron goes around in a circular orbit there, what's actually happening is you've got a wave which wraps around on top of itself. So if the circumference of the electron's orbit just happens to be exactly 3 wavelengths, then, so let's say we start right here. So there's 1 wavelength, there's 2 wavelengths, there's 3 wavelengths. So you can see that when it wraps around on itself, it wraps around in a way where it's going to interfere constructively with itself. Remember when we talked about constructive interference and destructive interference? You may have thought that that only applies to light waves, but guess what? It doesn't. It applies to all types of waves. It applies to sound waves, water waves, light waves, and even matter waves. Matter waves also undergo constructive and destructive interference. So if you have exactly 3 orbitals, then you're going to have constructive interference, which means you have a nice stable orbit. The electron can exist that way. Or over here, you see we've got 5 orbits. The circumference just happens to be equal 5 times the wavelength. And again, because it's a nice integer number, then we have, when it wraps around on itself and when the front part of the electron overlaps with the trailing part of the electron, they interfere constructively and it's stable. But over here, you can see we've got a non-integer number, okay? So we've, instead of having a nice exact 3 wavelengths, the circumference in this case is only 2.9 wavelengths. So when the front half of the wave comes here and it interferes with the trailing part of the wave, they don't interfere constructively, they interfere destructively, and the electron cannot exist in that state. Okay, so the electron will not stay there. It cannot. So that's the reason why you have forbidden zones. That's why when Coach Miller talked about the energy levels, he says you can be at n equals 1 or n equals 2 or n equals 3, but you can never be at n equals 2.5 or 2.5. This is the reason why. It's because the electrons are wave. And you need the full circumference there to be an integer number of waves. Okay, that makes sense, everybody? Okay, I'm going to assume it does unless you say otherwise. Okay, so here we have the different wavelengths. This is a picture that I took from a chemistry website, actually. And the way you know it's a chemistry website is because for the energy here, instead of saying HF, they said H nu. I don't know why, but for some historical reason, chemists, instead of saying F, they use the Greek letter nu. But it means the same thing. HF, H nu, it's all exactly the same thing. Okay, so we got the different energy levels here. And so when Coach Miller was talking to you about this, okay, he said that we've got an electron in the ground state. If somehow it gets kicked up to a higher state, like maybe it bumps into another atom and that kicks it up there, or maybe it absorbs light, whatever. There's lots of ways it can get kicked up. When it drops down, it's going to give off energy, and the amount of energy that it gives off is going to be equal to the energy difference between these levels. So this n equals 3 level, if only there was some way that we could calculate how much energy the electron has, we could actually come up with a number for an electron in the n equals 3 orbital has this much energy, whereas an electron down in the n equals 1 orbital, that only has less energy. So whatever the difference is between those two energies, that is how much energy the photon is going to have that's emitted when it drops down. Okay. So like I said, if only there was a way that we could calculate where we could actually come up with a number for what those energy levels are. Well, I'm sure you can guess what we're going to do right now. Okay. So we're going to do some calculations. Actually, what we're going to do is we're going to derive the formulas for how you calculate the energy levels for a hydrogen atom. it has to be hydrogen because that's the simplest case. That's the case that a high school student is capable of doing. If you want to do it for anything other than hydrogen, then the fact that you've got two electrons orbiting and they interfere with, they interact with each other. And so anything other than hydrogen is, the math is just way too complex. But hydrogen is something that could be done by a high school student. Okay, so we are going to derive the formulas that are used to calculate the energy levels for the electron of a hydrogen atom. Now, listen carefully because I'm going to do it a little differently than I've done it in the past. Normally, at this stage, I would tell everybody, turn to a new page in your notebook and start writing down everything that I'm about to do. That's not what I'm going to do this time. This time I'm going to do the exact opposite. I'm going to tell you guys not to write down everything that I'm about to do. The reason for that is because if you try to write down everything that I'm about to do, it's going to get really complicated. This derivation that we're about to do is definitely the hardest derivation we've done all year. There's a lot of complexity to it and a lot of steps. And if you try to write down every single step that I'm about to do, you're going to be so busy writing things down that you're going to miss the flow. You're going to miss, as I explain why we're doing what we're doing, you're going to miss all that because you're going to be so busy trying to copy everything down. So there are two reasons why I do not want you to copy everything down. Number one, everything that we're doing right now is being recorded. So you can always come back later and watch the recording, and you can pause the recording and write it down and then restart it and then pause it again. So that's number one reason why I don't want you to write it down. Number two reason why you don't need to write it down is because if I were to put this on the test that you guys are going to take on Friday of next week, I would put it down as an extra credit problem because it is pretty complex. Okay, so put down your pencils and just watch and just follow the flow and focus on why am I doing what I'm doing and make sure that I don't make any silly algebra mistakes, right? Okay, so here we go. We're going to start in the derivation. All right, so we've got an electron orbiting a proton, because you guys know that a hydrogen molecule consists of one electron, one proton, no neutrons, no nothing else. Okay, so you can kind of sort of think of it as it's a planet orbiting the sun, except we know that it's not really a particle, it's actually a wave, but that's okay, we're going to take all that into account. Okay, so if you think of it as a planet orbiting the sun, so this is the force that attracts it. So if it was a planet orbiting the sun, this would be the force of gravity, okay? But in this case, it's not gravity, it's the electrostatic force, but that's okay, we'll deal with that. And that is the one and only force that's acting on it. And that force is causing it to move in a circular path, right? So Newton's second law says F equals ma. And if it's moving in a circular path, we know that the acceleration is v squared over r, right? So far, I haven't done anything fancy, straightforward, okay? Now, as I just said, this force here that's attracting them is not gravitational force, it's the electrostatic force. Now, some of you might say, well, wait a minute, Mr. Hendricks, an electron has mass, a proton has mass, so is there not going to be gravity in addition to electric? To which I say, yes, you are correct. But if you look at the K value, the constant in Coulomb's equation, that constant is 9 times 10 to the 9th. That's 9 times 10 to the positive 9. Now, if you look at the constant in the gravitational equation, Newton's law of universal gravitation, the G value, capital G, that one is 6.67 times 10 to the negative 11. So the electrostatic force is 10 to the 20th times greater than the gravitational force. That's a 1 with 20 zeros after it. Okay, so the electrostatic force is so overwhelmingly greater than the gravitational force that unless you need 21 sig figs in your final answer, you can completely ignore gravity. It just is totally insignificant. All right, so we're gonna do this. So the force that's attracting, we know is given by Coulomb's law, K Q1 Q2 over R squared. okay? And we know that the charge on an electron and the charge on a proton are exactly the same, except one's positive, one's negative. So instead of Q1, Q2, we can just call it Q squared, okay? All right, so this force is equal to mv squared over r. It's also equal to k q squared over r squared, okay? So then we can then set them equal to each other. So k q squared over r squared is mv squared over r. So far I haven't done anything fancy, right? I haven't violated any laws of mathematics or any laws of physics, right? So what I'm going to do now is I'm going to just, I'm going to cancel out the r squared. I've got an r squared on this side and r on that side. Then, so this r cancels one of the r's. Okay, so I'm left with this. All right, so now I have one equation that has two unknowns in it. Because I know k, I know q, I know m, but I don't know r and I don't know v. All right, so I got an equation with two unknowns in it. So let me just put it up in the corner of the screen here. And I'll put it on hold temporarily. I need another equation. Where could I get another equation that relates v and r? Are the q's on the second equation accidentally squared? No. Oh, wait a minute. Oh, you mean up here? Yes, good point. Okay, that is bad. Oh, are you going to call that a wig point? But I mean, that was a mistake. Okay, so yeah, that's embarrassing. Thank you for catching that. Okay, oh, you're going to call that a wig point? You guys, you're so mean to me. Oh, you're going to make me wear the wig? Well, okay. I mean, it was a mistake, and it was a pretty bad one. Okay, so, okay, well, I actually just happen to have the wig right here. I deserved it. Okay, so, but the rest of it down here was correct. Okay, so thank you for catching that. All right, so let's try again. Okay, so I come down here, so I've got this equation, which is correct, even though I did make that intermediate mistake, that the rest of them were all correct. Okay, so now I need another equation that I can relate V and R. Okay, so I'm going to look at the fact that this electron is not actually a particle. It's actually a wave. And we know that the full circumference has to be either lambda or 2 lambda or 3 lambda or 4 lambda or 5, but it can never be 2.3 or 3.7. It has to be an integer number of wavelengths because it's a wave and we need interference to be constructive. Okay, so what I'm going to do is I'm going to say that the circumference of this circle, 2 pi r, has to be equal to n times lambda, where n can be any integer. It has to be a whole number integer, right? Okay, so given that, let's take de Broglie's equation, because de Broglie showed us that lambda was equal to h over mv. Okay, so all I did was replace that. So far, you know, nothing fancy here, just basic mathematics. All right, so now what I'm going to do is I'm going to take the v up here and the 2 pi r down there, so I'm just solving for v, okay? And now I'm going to square both sides. Now you might say, well, why are you squaring it? Because I'm thinking ahead. You see over on this side over here, I've got a v squared up here. So you can see what I'm going to do. I'm going to want to subtract this wherever I see v squared. So that's why I squared my v. Okay, so now I've got my two equations, two unknowns. So from this point on, it's no longer a physics problem. Now it's just a math problem, and you're good at math, right? Okay. So wherever I see a v squared here, I'm going to replace it with this thing that I know the v squared is equal to. And when I do that, I will get this. Okay, so k q squared over r is equal to m times this other thing that's equal to v squared. Okay. So now all I need to do is just simplify it. This is kind of messy here. I'm sure I can simplify that down. Okay, so I've got an m here and an m squared there, so that goes away. I've got an r here and an r squared there, so this guy goes away, leaves me one r there. Okay, and so now if I solve for r, there you go. We have just derived the equation that will tell you what is the radius of the electrons in a hydrogen atom at all of the different energy levels. So if we put n equals 1 in here, that will give us the lowest level energy the radius of the what they call the rest state. Okay, because we know Heisenberg, or we know H, we know Planck's constant, we know K, Coulomb's constant, we know the charge on an electron, we know the mass of an electron, 4 pi. So bingo, we have just derived the equation that tells you the radius of all of the different shells of the hydrogen atom. So n equals 1 is the rest state, but if we were to kick it up to a higher level, then we would just take n equals 2 and stick it in there, and n equals 3, okay? And so there we are. Okay, so Yasin is saying, what would happen if we use this equation on another atom? Well, okay, so think about it. We derived this equation assuming that there was only one proton in the middle here. If we pick some other atom, it's not going to have one proton in here. It's going to have 2 or 3 or 4 or 5. Okay, so that's going to change the attraction force. That's going to make the attraction force a lot stronger. And then the other problem that we're going to run into is that this electron is not just all by himself. In the other atoms, they have more electrons. And so all of those other electrons buzzing around, they interact with each other, and they make, the math is just is impossible for a high school student. Even for an undergraduate university student, the math gets impossible real fast. This is really graduate level mathematics here. Okay, so Anna wants to know what's the use of this equation. I'm glad you asked. Let's find out, okay? So, okay, first off, let's just make sure we understand. So if I want to know the n equals 1 level, I stick n equals 1 in here. If I want to know n equal 2, I stick 2 in here. And remember the equation says that it's n squared, right? Okay, so n squared, 2 squared is 4, 3 squared is 9. So if I actually plug in the numbers, I now have the radius of all of the different orbitals for the hydrogen atom, only the hydrogen atom, okay? What I really want to know is how much energy does the electron have if it's in the n equals 1 orbital, or how much it has in the n equals 2 and n equals 3. That's what I really want to know. So I'm going to have to do a little bit more math here, okay? So what kinds of energy could we possibly have? Well, we could have kinetic energy, we could have potential energy. Let's tackle them one at a time. Okay, so kinetic energy is of course 1/2 mv squared. And so that means that if I wanted to know what is the energy difference between the levels, because that's really the important thing. What is the energy difference between the levels? Okay, so if I could figure out what the velocity was for the electron that's in the n equals 1 level, and figure out what the velocity is for the electron when it gets kicked up to the n equals 2 level, okay, then the difference between those, that would be an important number. That would give me an idea of what is the difference in the energy between the two levels. Okay, so if I had some way of calculating what V1 and V2 were, I could calculate the kinetic energy at each level and calculate the difference. Okay, so that's pretty straightforward. But kinetic energy is only one of the energies we need to deal with. We also need to worry about potential energy. So let's think for a minute. When you guys hear the word potential, or when you hear the phrase potential energy, you no doubt think, oops, okay, hang on here, okay. Let's see. Okay, so what I've done here is I've just rearranged the equation. Let me come back to that later. Well, no, I guess I better not. Okay. Before we talk about potential energy. Okay, let's see if we can do some calculations. Okay, so from the previous calculations, we had this equation for v squared, you probably remember, okay? So do you see here that I can, in fact, come up with a number for what the velocity is for n equals 1 and n equals 2? Use this equation that we derived a couple minutes ago, stick in n equals 1, stick in Planck's constant, stick in all those numbers. So I can, in fact, calculate the kinetic energy for this electron at each level. Okay, so what I've done here is wherever I have a V2, I've taken this equation, stuck it in here with n equals 2. And over here where I have a V1, I've taken this equation, stuck it in only with n equals 1. And then I did a little bit of simplification because each term has an h in it, and each term has an m and a 4. Okay, so basically this equation right here, which I do not expect you guys to memorize, you can write this down in your notes. and it's in the book as well. This equation tells me what is the difference in the kinetic energy between this electron up here and this electron down here. Okay, but now, as I started to say before, kinetic energy is only one of the energies we need to worry about. We also have to worry about potential energy. So when I say potential energy, you're going to probably think MGH, okay? So can we use MGH to calculate the potential energy in this case? Well, no, for two reasons. One is that this is gravitational potential energy, and we've already decided that the gravitational force is 10 to the 20th times weaker than electric. So gravitational force is completely negligible, okay? All right, so then we say, okay, we can't use gravitational force. So what we're going to do then is we're going to say, okay, work is equal to force times distance. So if I could figure out how much force I had to apply to push this electron from this level to this level, and then take that difference, take it multiplied by that distance, then you might be tempted to say that that would be a good way to calculate the potential energy difference between the two levels, okay? There's a problem with that, okay? This equation over here, F equals, or the work equals force times distance, that equation only works if the force is constant. In this case, the force is not constant. The force acting on this electron here is a lot stronger than the force acting on this electron here, because remember how the force is proportional 1 over r squared? So if I take this electron here, if I push it from this orbital to this orbital, the force is not constant. Therefore, I cannot just say that the work is equal to force times distance. I'm going to have to use calculus. I'm going to have to say that the work, which is the potential energy, is the integral of the force dx times the distance. Okay, so what I'm going to do for the next 2 minutes is going to have to use calculus. Now, many of you are good at calculus. I understand you guys did really well on the exam last week. So congratulations, most of you did really well. That's what Ms. Strong tells us. Okay, so for the next 2 minutes, I'm going to use something that those of you who are in calculus will understand. Those of you who are not in calculus won't. I will not put this on the test, so don't worry. I just want you to watch and just see that it is definitely doable. Okay, so the force that we're talking about here is Coulombs force. So wherever I see an F, I replace it with K Q squared over R squared. Okay. Now, those of you who are in calculus know that I can take the constants and pull them out front. Those of you who aren't in calculus, don't worry about it. Just trust that the calculus students are going to check, and if I make a mistake, they'll let me know. And by the way, I'm watching the comments window. So those of you that know calculus, if I make a mistake, be sure to let me know. Now, you've noticed I've done a change of variables here. I changed it from dr to d, from dx to dr. But those of you in calculus know that's legal to do. Okay, so now I'm going to actually perform the integral. So going from this step to this step is something that those of you who aren't in calculus, you have no way of verifying this, right? But those of you that are in calculus, did I do it correctly? Actually, tell you what, I'm going to pause for a second. Several of you are in calculus. So tell me, did I do it? Is the integral of 1 over r squared 1 over r? And actually with a negative? Okay, it is. Okay, so now those of you that aren't in calculus, it's time to wake up again, because we're finished with the calculus now. Okay, so I now have two rather complicated looking equations, but hopefully you guys have seen that what I did is completely legal. So Izzy's asking what happened to the negative. All I'm interested in is the difference between the levels. So it's okay if I ignore the negative. Yeah. Okay, so I have these two equations that can tell me what is the kinetic energy and what is the potential energy at n equals 1 level and at n equals 2 level. Now I'm finally ready to calculate the actual energy. We can now calculate how many joules of energy the electron has if it's in the n equals 1 level for a hydrogen atom. And we can calculate how many joules of energy it has if it's in the n equals 2 level for a hydrogen atom. Okay. So what we're going to do is we're going to take these two equations that we just got through deriving, and we're going to take this other equation that we derived a couple minutes ago, and we're just going to put in the numbers and see what happens. Okay, so let's see, what did I do here? Oh, okay, so what you see right now, this tells you the change in energy from n equals 1 to n equals 2. Okay, but I hope you realize it doesn't have to be n equals 1, n equals 2. It could be, I could talk about the difference between n equals 1 and n equals 5, or I could talk about the difference between n equals 2 and n equals 8. It works just as well. Okay, so what I do is I recognize the total change in energy is going to equal the change in kinetic plus the change in potential. Okay, and if I put in the numbers, if I say I want to know what is the energy given off if the electron goes from the n equals 3 level to the n equals 2 level. Okay, so what I can do is I can take n equals 3. I can plug it in here to find out the radius and stick it in here. And I can plug it in here and I can calculate what is the energy of the electron at the n equals 3 level. And then I do the same thing for n equals 2. I stick n equal to wherever you see an n here, I replace it with 2, and I can put in the numbers. And what you find is that the difference in energy between n equals 3 and n equals 2 works out to be 3.3 times 10 to the negative 19 joules. And then I say, okay, so if that's the difference in energy, then when the electron drops from n equals 3 to n equals 2, that's how much energy the electron is going to give off. That's how much energy the photon is going to have. And if I know that E equals HF, or HC over lambda, which is the same thing, I can actually calculate the wavelength that is given off. Okay. Now, some of you are saying, okay, nice, but again, so what? What you're about to see right now is earth-shatteringly important. What you're about to see right now is what convinced Einstein that God really does play dice with the universe after all. Because if you were to take a gas tube like the ones that I have in my classrooms, you guys saw these, okay? Take a gas tube and excite it with high voltage and look at the light that comes out of it. If you take that light and send it either through a prism or a diffraction grating, you can see the colors of the light and you can calculate the wavelengths of the light that are given off by a hydrogen atom. And guess what? Okay, you are going to see the hydrogen atom gives off light that has a wavelength of 656 nanometers, exactly what quantum mechanics predicted. Okay, now there are many different levels here. If we look at the energy that's given off when an electron falls down from n equals 4 to n equals 2, we can use the equations that we just derived, and we can calculate that the energy is going to be 4.09 times 10 to the 19. We can then take E equals HF, and we can calculate the wavelength, and we get 486, and guess what? It matches, okay? And do the same thing, n equals 5 to n equals 2. We can predict, using quantum mechanics, we can predict that the light given off would be 434 nanometers, and when we perform the experiments, guess what? We find that light is given off at 434 nanometers, okay? This is astounding. Remember how Einstein, he fought tooth and nail against quantum mechanics. Quantum mechanics was just too strange. He did not want to accept it. But when Louis de Broglie and Niels Bohr and a lot of other people, when they took quantum mechanics and they did the math that you and I just did, and they predicted what the light would be that's given off, and they compared it with the light that was actually given off, and it matched beautifully. So even Einstein had to say, well, I guess God really does play dice with the universe after all, because this is just too beautiful. The fact that the fundamental quantum mechanics, starting from scratch, starting from pure theory, you can come up with these numbers and they match perfectly. Okay, and then if you're wondering where this 410 comes from, well, okay, this is where the 410 comes right here. The 410 line, that comes when the electron falls from the n equals 6 level down to the n equals 2 level. Okay, so personally, I am in awe when I see this. I just, the fact that you can start from pure theory and do the calculations and come up with something that matches the experiment so incredibly well is just, to me, just awesome. Okay. Now, you might be wondering, in all of these cases that we did here, it was always the electron was falling from some higher level down to the n equals 2 level. And you might say, why did it stop at the n equals 2? Couldn't it fall all the way down to the n equals 1 level? And the answer to that is yes, it could. And in fact, if you do the math, okay, here are the numbers that you get, okay. Okay, so it is in fact, or it does in fact happen that electrons do go from the n equals 3 all the way down to n equals 1, or they go from n equals 5 all the way down to n equals 1. But when you do the math to calculate what the wavelengths are, what you'll find out is that the wavelengths for all of those transitions, they're all in the ultraviolet. So when you look at the colors, you're not going to see them because the human eye is not sensitive to ultraviolet. Okay, the only transitions that give off light in the wavelengths that the human eye can see are the ones where they fall down to the n equals 1 or n equals 2 level. Okay, so in your chemistry class, you may have seen a diagram similar to this. And so this is where it comes from. It can all be calculated based on first principles. Now, Izzy was asking about the negatives. And so here you see a bunch of negatives too. The negative really is, it's all relative. We should talk about it because every year students always ask about this. So according to this, the way scientists have defined things, energy levels are always negative. Okay, and the lower they are, the bigger, the more negative they are, and the higher they are, the less. So let me explain why they did this. They had a reason. Okay, let's suppose I take my cell phone and I put it on the table and I ask you how much potential energy does it have? You're probably going to say it has 0 potential energy. And I'm going to say, yeah, but what if it fell off the table onto the floor? Then, so doesn't that mean that it actually had some potential energy when it was sitting on the table? So do you see that when I define potential energy, I have a choice where I could put the reference level. I could define the reference level to be at the tabletop, or I could define the reference level to be on the floor. Or if I wanted to be really wild and crazy, I could define the ceiling as my reference level. I could say that the phone has 0 potential energy when it's at the ceiling, and if it's down anywhere below the ceiling, it has negative potential energy. And I can do that and I can get away with it because all we really care about is the difference in the energy levels. Okay, so if I'm talking about, I've got -5 joules of energy here and I've got -10 joules of energy here. And so what's the difference? The difference is 5. Okay, and so if I want to know how much kinetic energy this is going to have, all I have to do is whatever is the difference in the potential energy here, that tells me how much kinetic energy it's going to have. So my choice of reference locations could be the floor, could be the tabletop, or it could be the ceiling. And so what scientists have done with whenever you have an electron orbiting a nucleus, how do you pick the reference level? You could say, well, let's pick the reference level to be the surface of the proton. But how big is a proton, and is that really the appropriate place? So basically what scientists did, in fact, not just basically, what scientists did was they said, okay, we are going to pick our 0 to be the point that is infinitely far away. We're going to say that this electron has 0 potential energy when it's infinitely far away. And if it's anything less than that, it's going to have negative potential energy, just like my phone does if I define my reference level to be the ceiling rather than the floor. So that means my phone is always going to have negative potential energy, but that's okay because all I really care about is the difference. Okay. So I hope that kind of explains why we deal with negative energies here. Okay, so in your homework tonight, if they were to ask you, what is the energy of a photon that's given off when an electron when it drops from the n equals 4 level down to the n equals 3 level? Do you realize that this chart right here, which by the way I took out of the book, so it's in the book, this chart will give you the information you need. So you come up here, so n equals 2, n equals 3, so here's n equals 4. And you can see over here that the total energy, now this is not just potential, this is potential plus kinetic. So the total energy of the electron when it's in the n equals 4 level is 0.85 electron volts. And the total energy of the electron when he's in the n equals 3 level is negative 1.51 electron volts. So if an electron drops from n equals 4 to n equals 3, then the energy given off will be whatever 0.85 minus 0.1 or 1.51 is. Okay. Okay, Izzy, I'm not sure what you mean by that. I hear you and it makes sense, but I deserve to feel included. Not sure what you mean by that, but okay. Oh, okay, all right. I will, never mind. Okay, so you guys see, so in your homework tonight, if they ask you to calculate the energy of a photon that goes from n equals 6 to n equals 2, you guys know how to do it? Just use this, okay? All right. Let's see, what else? Okay. The energy levels that you just saw up here, okay, notice they didn't use standard physics units for that. They used electron volts, okay? Well, these right here, these are the equations that they used. Up at the top here, these are the equations that we derived earlier, okay? If you really want to have fun, if you want to know the energy of an electron when it's in the n equals 5 level, just take 5, stick it in for n, calculate what the radius of it is, stick that into these equations over here, okay? And you can calculate tonight's homework using these equations if you want, but the author of the book did you a favor. So the author of the book took all of these numbers and did the calculations for you. So it all boils down to one of these two equations. And so these are the only equations that you really need in tonight's homework. You do not need these big, ugly, complicated equations that we derived, okay? These equations down here are a simplified version of these guys, okay? So if you want to know how many joules of energy an electron has when it's in the n equals 7 level for a hydrogen atom, just take negative 2.18 times 10 to the negative 18 and divide it by whatever that n is. So if you want to know the n equals 7 level, stick in n equals 7 here. And this equation right here will tell you how many joules it has for that level. And then if you want to say, okay, well, it's going to jump from n equals 7 down to n equals 4. So then stick in n equals 4, do the math. And so now you know how many joules of energy it has at n equals 7. You know how many joules of energy it has at n equals 4. Just take the difference, and that will tell you how much energy the photon will have that is emitted when the electron falls. Or, you guys know it also works in reverse. If I have an electron in the n equals 4 level, and I want to kick it up to n equals 7, this exact same number, that'll be how many joules of energy the photon needs to have in order to kick it up, okay? So this upper equation right here is the one to use if you want the energy level to be given in joules. If, on the other hand, you prefer the energy in electron volts, which will be the case for many of the problems you're going to have tonight, you're going to find out that people who do this kind of stuff day in, day out, they actually work with electron volts more often than they do joules. It's a little more convenient unit. It's not a standard physics unit. If you're doing E equals HF, do not put E in electron volts. It has to be in joules, okay? But either one of these has worked. So write these equations down. Actually, they're in the book, and I know you always read the book, right? Or you can just write these equations down. These two guys right here are all you need. You don't need to know the big, ugly, complicated ones from which these guys came. Okay, So let's do one more problem. And this one here, I'm just going to point out what they did in the book here. Okay. So example problem number 1 in the book, very similar to what you're going to see in the homework. They're saying that a hydrogen atom absorbs energies, causes the electron to move from the lowest level, the rest level, n equals 1, up to the n equals 2 level. So they're asking you to find the energy of each of those 2 levels, and then take the difference in order to find out how much energy got absorbed by the atom. Okay, and you'll notice that they decided they wanted to work in electron volts. The question up here didn't say whether to give the answer in electron volts or joules. So the way the question is worded, you could have done it either way. And the author of the book decided he wanted to do it in electron joules, or electron volts, Okay, so what we do is we use this equation here. We say the energy of the n equals 1 level is 13.6 divided by 1 squared, which works out to be 13.6. And we say, okay, the energy of the n equals 2 level is 13.6 divided by 2 squared, which is 4, obviously. Okay, so these 2 numbers here, those are the energies of the electron at the n equals 1 and n equals 2. So now if we just take the difference between them, that will tell us the energy of the photon that's needed to kick the electron up. Or if we were to do it in reverse, if we started out at n equals 2 and dropped down to n equals 1, this would still be the same number. That would be how much energy the photon has. Okay. Now, in problem number 1, they stopped at that point. But in some of the homework problems, they might take it to the next step. They might say, what is the wavelength of that photon? Okay. So if they were to do that, if they said, okay, now we know the energy of the photon, what will the wavelength of the photon be? Well, we can take E equals HF, which is a very important equation that you should all know by now. But you do have to be careful, because when you're using E equals HF, you cannot use electron volts. It has to be joules. But that's easy. I mean, by now, you guys should be able to transfer back and forth between electron volts and joules just as easily as you do from centimeters to meters, right? So the conversion factor between electron volts and joules is given right here. So we take our 10.2 electron volts, we convert it into joules, we stick that into here for delta E, which I've rearranged here. So HC over delta E is 122 nanometers, which, as I mentioned before, that is not in the visible part of the spectrum. That would be ultraviolet. Okay, so the human eye cannot see that. It's still there. It's just the human eye would not be able to see it. So these are the types of problems that you're going to have in tonight's homework. You do not need to do the derivation. I think it's important that you see the derivation. I think it's important that you realize that there's no magic involved here. And as long as we stick with the hydrogen atom, all of the math that you need in order to, if you wanted to do it from scratch, it's all stuff that a high school student could do. You don't need any advanced level above what a high school student could do. Okay. Now, if you go to other atoms, if you go to helium or neon or lithium or whatever, then high school math is no longer going to be adequate, because then you've got so many protons in the nucleus, and you got so many electrons buzzing around in the outer shells. The math now becomes so complicated that a high school student can no longer do it. But as long as you stick with hydrogen, then it is easy enough for a high school student to do. Okay, so Hiram is asking, will the derivation be on the test? So my answer to that is, if I were to put it on the test, then number 1, I would put it on as an extra credit problem, not as a required problem. And number 2 is, all I would ask you to derive is the equation that tells you what is the radius of each of the different orbitals. I would not ask you to derive the formula for the energy of the different levels. And the reason I wouldn't do that is because in order to do that, you need to know calculus, which some of you do, but most of you don't. And so therefore it wouldn't be fair. If I ask a question that some of you know how to do because you know calculus and others of you don't because you don't know calculus, that wouldn't be fair. So if I did it, I would stop at the point where all you do is you calculate what is the radius of each of the different levels. And I would also put it on the extra credit problem. Okay, well, then let's talk about tonight's homework. So problems 1 through 8 in chapter 28. You don't need to read anything in the book beyond that. And even the stuff ahead of that, the first several pages in chapter 28, I would like you to read through them, but you don't need to spend a lot of time fixating to make sure that you understand everything. The only stuff that I really worry about is the calculations, the equations that calculate the energy of the electron at each of the different levels in the hydrogen atom. Those are the only things that I really truly care about. Okay, so Andre is asking for a reminder of what the secret word was. Okay, so secret phrase actually. Okay, so right here, the secret phrase, the force will be with you always. That's the secret phrase. Okay, before I turn off the re-recording, are there any questions? Not seeing any questions. Happy Teacher Appreciation Week. Oh, thank you. Happy May the 4th. Okay, so going once, going twice. Oops, I covered up my chat box. Nope, I didn't see anything. Okay, so we're here again. Going once, going twice. So